Go ahead.
All right, very good. Welcome back. This is the Test 4 review, chapters 12 through 15 for Monday, April 13th. Test 4 is due on Learning Suite tomorrow night, Tuesday, by midnight. Do it well ahead of time. They've had, again, some problems with Learning Suite, so make sure you're well ahead of that time there. And all you need to do is upload your answer sheet, just like before. Do full 40 multiple choice questions over these last 4 chapters. Homework 15 is also due tonight, even though we finished the topics in chapter 15 already. And then quiz 10, the last quiz, yay, is due Wednesday. Make sure you upload that by Wednesday night. It's on Learning Suite there. So very good. So what I'd like to do today is go through some problems that review all the problems, reactions from chapter 12 and 15. That's where the new reactions are. Remember, chapter 12 is the reduction oxidation reactions, and chapter 15 is the radical reactions we just covered. And then 13 and 14 are the spectroscopy, mass spec, IR, and NMR that we just finished. So let's move over here and work some of these problems. If you'd like to pause the video and go through those, see if you get them right. We've got a few up here. This is from chapter 12. These are mainly all reductions. No, we have a couple oxidations down there. So let's see, how do you do on this one? An alkene with hydrogen, yep, just goes to the alkane. So very good. Same thing here, although we have 2 methyl groups, 1,2 dimethyl cyclohexene, and when it undergoes the reduction, you see, we've got stereochemistry here. So the hydrogens both come from the same side, either both from the top or both from the bottom. So make sure you draw some stereochemistry there. Both the methyls are back in this case, and they end up cis to each other because of the syn addition, part of the mechanism of the hydrogen absorbed on the palladium surface. They both come down together. You can't tell here, this first example, there's no stereochemistry, but here you have the stereochemistry, and cis would be the correct one. Here's another reducing agent, lithium aluminum hydride, and the key there is the hydride. This hydrogen with its pair of electrons can come off. The aluminum is negatively charged. One of the hydrogens can come off, so a little on the mechanism there. It is known to be SN2. And again, what do we get? Alkane from the alkyl chloride. Kind of a similar idea here. The hydride can open up the epoxide either at the tertiary position or the primary. But if it's SN2-like, where's it going to open up? Correct, right there. And then we have to have water here as part of this, the lithium aluminum hydride, and then quench with water at the end. And what do we get? We get the tertiary alcohol. What? Gets the hydride added at that primary spot. All right, here we have an alkyne with hydrogen and palladium. This is the active catalyst, so we get complete reduction there of both pi bonds. And even if we don't show excess here, if you have the active catalyst, over reduction will be the main product there. But if we have the poison catalyst, Linlar, the calcium carbonate, lead acetate poison, and that's a lot to draw out. You can just say Linlar. Or even just Linlar with the hydrogen. Some people asked about that. Do I need to include the palladium? That's okay. If you say Linlar, we assume you've got the palladium in there. You can't just have the poisons. The palladium is still the active thing there. But the key here is what? We get the cis product. Okay, the 2 hydrogens again adding syn. If we want the trans, we use a different reducing agent. Sodium and ammonia. And this will give us the trans product here. So we say those 2 sets of conditions are complementary, giving the cis versus the trans. Okay, we also have a couple oxidations, MCPBA, metachloroperbenzoic acid, with the trans alkene will give us what? The trans epoxide. And that is chiral. It gives a pair of enantiomers. You should say DL. You can draw them both out, and that's attack either from the bottom or the top, giving you the trans. Notice the stereochemistry of the two methyls from the starting material is transferred into the stereochemistry of the product. We call that a stereospecific reaction. Similarly here, with the tri-substituted alkene, we would want to show some stereochemistry there. But again, this is a DL pair. We have a stereo, both spots here. And because of the small ring here, it's always cis-fused on there. It would not make sense to draw one down and one up. Can't make a model of that. too rigid there, but yeah, both epoxides available there. Okay, let's get some more reactions up here. Chapters 12 and 15, those are the two reaction chapters. Let's get a couple more up here. How about this one? Osmium tetroxide. And let's see, how about an alkyne with ozone? And how about an alcohol here with chromium oxide and sulfuric acid added? And how about those same conditions applied to secondary alcohol? And let's see, how about ozonolysis, dimethyl sulfide, the quenching part there, the ozonide. If you leave that off, we'll give you full credit, and sometimes it's not thorough on a quiz or a test, but yeah, the ozone, the O3 is the key thing here. Oh, and how about that same alcohol, but with PCC? And how about this one? We've got an allylic alcohol, and we're going to use the plus form of diethyl tartrate, DET, and titanium tetraisopropoxide, and we need terbutyl hydrogen peroxide. That whole mixture is the sharpless asymmetric epoxidation. I'll just let you say sharpless, but on a test, if we're showing you the transformation, we'd show these three key ingredients. You need each one of them in there. But if you're providing the reagents for a product in mind, you can just say sharpless. And remember, you don't need to know which enantiomer goes with which form of the diethyl tartrate. Well, let's see how you do on these 7 problems here. Pause if you'd like. Okay, and we're back. Osmium tetroxide here on this one. We'll give what? The diol. And again, it's syn addition there. The diol, both alcohols are on the same face. And so the methyls are pointed back. I've got 2 methyls there. Don't leave off that second one. But yeah, that would be it. And it's achiral because of the symmetry there. How about ozonolysis here? Ozone O3. And I like that lysis name, part of the name, treatment of ozone. The lysis means to cleave, right? We're cleaving the bonds here. The triple bond being cleaved will go to the carboxylic acid. What happens to the other carbon? It becomes formic acid. So on the other side, say that one. If it's terminal here, the formic acid is lighter weight. Usually it's the bigger part over here that we are more concerned with. Anyway, so we got primary alcohol with chromium oxide, sulfuric acid. That makes what? That makes chromic acid in situ, we say. Within the reaction flask, if you add chromium oxide with sulfuric acid, you make the chromic acid. And that's a strong oxidizer, so primary alcohols are oxidized to what? All the way to the carboxylic acid. And keeping these straight, again, these are all oxidation reactions, right? You see a lot of oxygen in these reagents. That's a way to keep track of it. Secondary alcohol now. What do we get here? Ketone product. And it stops at the ketone. Why? Because we already have 2 carbons on there. So removal of the 2 hydrogens, conceptually, that's not how the mechanism, actually, well, they kind of go step by step. We showed you part of this mechanism here. It forms a chromate ester, pull a proton there, flow the electrons into chromium. I've never put that on a test, so don't worry about the mechanism of it. But the effect, primary, secondary, tertiary, no reaction under these conditions, because there isn't another hydrogen there to pull off to do the oxidation. So part of the mechanism helps you keep that straight. Ozonolysis, on there we showed a quenching reagent. We want to be safe there. Just molecular scissors there across the pi bond. So we'll get an aldehyde in this case for the fragment on the right, and then the two methyls there, the fragment on the left, becomes a ketone. Okay? PCC, pyridinium chlorochromate, stops at the aldehyde. Very important reaction to do the partial oxidation here. This is actually the intermediate in the chromic acid reaction. And in the presence of stronger acid and water, you can hydrate this, form another chromate ester, and then pull the proton there, and then you go to the acid, but not with PCC. That's anhydrous conditions. There's no strong acid. It's the pyridinium chlorochromate, and the chloro group attenuates the reactivity of chromium 2. Stop the aldehyde. All right, the diethyl tartrate here, the chiral ligand on the titanium will form the epoxide here. And I know from the mnemonic device how to figure out which enantiomer is which. But if you drew this one down or the one with both of those stereocenters up, we'd still give you full credit. Okay? And if it's part of a synthesis thing, you can just pick whichever chiral DET ligand you'd like there for that series. Okay, so how do you do on that group? Hopefully okay. I've got one more group for chapter 15 here. Let's see, how about this reaction with chlorine with an alkane? Shine light on it and keep it at room temperature. How about this one? Bromine, light, room temperature on that same substrate. And how about cyclohexene with NBS and shining light on it? And how about this alkene with HBr and the peroxide initiator? Oh, and one more. How about styrene? What's the pH mean here? Not the pH scale. Little p, little h. That stands for benzene, or the phenyl group. So we have vinyl benzene. Okay. This whole molecule is called styrene, though. And we're not going to have any other reagent in there except the initiator. So give those 5 reactions a shot. Do it on your own without looking at your notes, maybe, to see how much you remember from chapter 15. Okay, and we're back. Let's see, what are we going to get here? Chlorination of an alkane. We're going to get some secondary chloride product. Notice these two methylenes, if you do the chlorination on either one, you get the same monochlorination product. How do we know it's monochlorination or room temperature? So we're limiting the energy there. But we're going to also get this product, right? The primary one. Chlorine is not selective. Why? Versus bromine. Bromination is highly selective because both steps of the propagation mechanism are endothermic. That lets you differentiate between the transition states better, leading, in this case, to the secondary product only. Whereas the 2 propagation steps of chlorination are highly exothermic, so those transition states compress, and there's really no way to control very well the selectivity in that case. So bromination, always just do the mono position, room temperature, and the most substitute spot here is the secondary position. There's no shifts involved in halogenation because it's a radical process, and remember those radicals don't do the shifting the same way as carbocations do. Let's do this one over here next. So we have NBS. So we get the allylic bromination in this case, okay? And this is just a source of bromine. And you can actually do this reaction with molecular bromine, Br2, provided you keep the concentration low. But this is the same reagent used to what? Dibrominate, halogenate alkene. So you need to control this, and then the light, what makes this a radical pathway? And under these conditions, we just get allylic bromination. Okay. Now, here we got HBr with an alkene, but we're under, what, radical conditions? So what product do we get? That's right, the anti-Markovnikov product. That should be contrasted with chapter 10, just using hydrobromic acid on its own without the catalyst here. What do we get in that case? Right, the Markovnikov product. So this comparison is important for the final coming up. This reaction won't be on test 4, but it probably will be on the final. Okay, and we say these conditions are complementary because they give different regioselectivity for the products. Anti-Markovnikov and Markovnikov. All right, very good. Hopefully you did okay on those problems. I'd like to work a couple of NMR problems now on the board. And here we'll just use the line list data, and I'll take you through the process of figuring these things out here. So here's a compound, C9H12O, okay? And the NMR, proton NMR, we have at 0.9, 3 hydrogens, triplet. And then we have at 1.9, 2 hydrogens, quintet. So a lot of times the problems are just like this. If you worked enough homework problems, see a lot of times they don't actually show the spectra, we'll just show the line listing of the NMR data. But that's very rich in information, right? The multiplicities and the number of hydrogens there. There's 5 signals here, sorry. 2.6, 2H triplet, 7.2, 3H multiplet, and 8.1, or 8.0, 2 hydrogens doublet. There's some other information here. In the IR, we're told this is signal at 1720 and 3000. And in the mass spec, we have a molecular ion of 136. Okay, what's the structure? What's the compound? We've got to come up with a structure that's consistent with this data. So let's see, we've got quite a few signals here. This is a little bit harder problem, I'd say. Maybe not as hard as problem 3 on quiz 9. But from that, let's see, where should we start? Well, we're given the molecular formula, which is nice. We could probably come about that looking at 136 here. That's a good guess there. We can combine that with some IR information. The 1720, what's that? Yep, carbonyl. We've seen it many times with esters and ketones, whatever. What's the 3000 here in the IR? Is that an alcohol? No, that's probably just CH stretch. Okay. And looking at the proton NMR, we've got different types of hydrogens, right? How many total hydrogens do we have here? Well, add them all up. I think that's 12, right? 5, 6, 7, 8, 9, 10, 11, 12, yeah? So there they all are, and then from the patterns there we can figure it out. Right here, these two, we should be able to figure out something. There's what? 3 hydrogens, 7.2, 2 at 8. So what? That's a total of 5 in what range? That's right, it's in the aromatic range. So we've already got a big piece of our molecule here. We've got a monosubstituted benzene, probably. Okay. And these are shifted a little further downfield at 8. So that might tell you something about where this carbonyl might be located. So we're already kind of figuring out a few key things here. Let's see, what else can we say here? We've got CH3 here at 0.9, so what's that probably? Well, that's probably this, right? A terminal methyl group for that. And then you got 2 methylenes here for 2 hydrogens, and one's at 2.6. That should tell us something too, proximity-wise. And we're thinking about a carbonyl after all, so maybe these 2 right here, and then they have 2 neighbors, so maybe those 2 are right there. So yeah, that would make that a triplet, you see, okay? And this would make this a triplet here, okay? So what's this one here? Well, that might be the same thing for this guy that's a quintet. So what does that look like? These three pieces here probably look like this. A propyl fragment, right? That would be consistent with that. And the shift here that's furthest downfield is 2.6. So what is it next to? Well, could it be next to an oxygen like that? Maybe an ether? Okay, because we've got one oxygen probably, right? But that would be around 3.5 delta, okay? But if we're next door to a carbonyl like this, then these two hydrogens are where? Yeah, 2.6 delta. That would make a little more sense. And that's basically it, right? We don't have much else to do here except to put these fragments together, okay? So hopefully you see how we can piece this together one thing at a time. What we arrive at is this structure here. And we have the propyl group and we have the benzene group for this ketone here. There's another piece of data I kind of omitted at the top. What can you learn from this molecular formula right away? How many degrees of unsaturation do we have? How many double bonds or rings? Well, carbon, 9, the max would be what? 20, right? So 20 would be the max number of hydrogens when fully saturated. 20 minus 12 divided by 2, degrees of unsaturation, 4. Do we have 4 double bonds and rings added up? Yeah, right here. The benzene, right? We've got 4, 5. Wait a minute. Are we off here somehow? How many degrees of unsaturation do we have? We got the 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. We've got 1 degree of unsaturation. 1 for the ring. It looks like 5, doesn't it? Are we off here somehow? How many degrees of unsaturation do we need? And we got 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, wait a minute. Were we off here? Maybe we were. Double check that. Let's see the mass spec 136. Did I make a mistake here? What should that be?
It should be 148.
So this should be what? Not this, right? What should it be?
148.
12 and 16. So yeah, this should be 148. Sorry about that. Don't know why I wrote that down. But we figured this out, between Isaac and myself, just now. Looking at the degrees of unsaturation now, and if we arrive at the structure, yeah, making sure things are internally consistent, which I should have checked to begin with, sorry. We've got 4 here for the benzene, and then 1 for the carbonyl, so this should be 5. And with the correct formula, the correct mass, all these are still the same. I don't think we're off there. But is this correct now? Yeah, 10, 148. And at this 10, what's the max hydrogen? It's 22, right? 22 minus 12 gets us to the 5 divided by 2. Yeah. So I think we are good. Let's try to do one more. That's a good one. Let's do this one. NMR looks like this. Delta 0.9, 9 hydrogens, singlet. 3.2, 2 hydrogens, triplet. 3.4, 2 hydrogens, singlet. 3.7, 2 hydrogens, triplet. Mass spec, hopefully I got this right. 152 and 150 and 115, and there's 35% of that one, 12% of that one, and 100% of this one. So we've got a base peak that's not the molecular ion, it's a fragment. And usually if it's 100% for an ion, we'll show it. But these are the molecular ion peaks, so that should tell you something right away. IR, 12, 11, and 3000. And I think that's it. Let's see. So how are we going to start this problem? Let's see, we're not given the molecular formula here, which is a little bit different, right? But we're given the mass spec data, and so which is the molecular ion here? We got a 152 and a 150 here. 12, 11, we don't have a 17 here, so probably no carbonyl. If we got a carbonyl, it'll always be large at 17, we'll always show that. 3000 again is probably just CH. Oh boy, that's about all we got out of that. What do you want to move on to here? Is there anything here you can see right away that might be in this structure? Let's see. And this is kind of the key here, 35 to 12. What's the ratio here? Oh, it's 3 to 1, right? And if you got a ratio 3 to 1, it's what, 2 mass units apart? This is probably the molecular ion peak right here, and the 152 is probably the N+2 peak. And this is indicative of what? The presence of chloride. Okay, and you saw that on quiz 9 also. So what can we figure out there? 150, if we have the chlorine 35 isotope, and we might be able to, figure this out. So if we got 150 here, how many carbons do we have? How about 8? If we have 8, that's 96 plus 35 for the chlorine, plus 15 for the hydrogens, and we can just add up these hydrogens. We're given the integration there, so we got 15 here. But this mass, if we're figuring for C8, so we're trying to figure out the number of carbons for our structure, that's 146. And that's quite a bit off. 4 units, are we missing 4 hydrogens? No, that wouldn't make sense. Anything else there? No, that probably is not it. Maybe it's better to back up. How about C7? We have 84 plus 35 plus 15. We get to 134, which means what? We might have, how do we get up to 150 then? Oh, plus 16 for what? Oxygen. So we get up to 150. So there, maybe we've got oxygen. How else do you know you might have oxygen? We don't see carbonyl in the IR, but what do we see? What's this 1211? Yeah, that could be carbon-oxygen stretch. That's the region for that. So it might be an ether. How do you know it might have oxygen? You've also got a lot of things down here around 3 delta in the proton NMR. So you've got 6 hydrogens there. You've got, some things maybe next to this chlorine that'll shift things down there to 3.5 or so. But if we have an oxygen, then we've got the capability to come up with the correct shifts there. So I think that's kind of a key here, figuring out we've got 1 oxygen, 16 to get to 150. And what's the 152? That's the chlorine 37 isotope, okay? That's less abundant, okay? So let's begin to piece things together. 3H singlet at 0.9 delta. What do you think we've got? Right, terbutyl. It's the easiest thing. They're all the same, spinning around makes all those 9 hydrogens equivalent. And then what else do we have here? 2H triplet, so CH2, and it has CH2 next door here, and it's got some heteroatom on it. Okay, so those 2 with 2 neighbors right there. And then we've got a singlet here for 2H, so how do we come up with a singlet? Well, maybe we're next door to a heteroatom and next door to something else that might have no neighbors, okay? And that something else could be this terbutyl. So we've already got an idea there for what those 2 could be to come up with this pattern to be a singlet. This X group, the heteroatom group, can shift those down to around 3, right? Then we got a similar thing here, another X, CH2, next door to what? 2 hydrogen. So it looks like combining these 2, we've got a CH2, and then some X and X on the other side, right? So can we combine these and begin to think about things? Well, the oxygen's nice because it's what? Divalent. We can have two groups attached to it. So how can we have this one here? Maybe this R group is our tert-butyl group. So how about this? The tert-butyl, and then we have a methylene there, and the oxygen there. That would account for the 9 that are a singlet, and these 2 that are shifted what? Down here at 3.4. What about that? And then we've got what? The ethylene fragment, and that's these 2 here that are both triplets, okay? And kind of hard to tell which is which here. We've got one at 3.2 and one at 3.7, and then we put our chloride on there. Would that be consistent with it? Yeah, okay. It's important to consider maybe some other ones and maybe determine, why they're not the correct one. So for example, why is this one not the correct one? Couldn't we just move one of these methylenes over here and have our ethylene fragment right there? What's inconsistent about the data here for this one? Yeah, these 2 right here, alpha to 2 electronegative groups, those would be shifted down around 5 ppm at least, okay? Remember, it's an additive effect. These 2 would be kind of similar there, although this one, though, if this is 1 carbon away from this group there, this one would drop down to 2.6 or 2.5 or so. So you see, shift-wise, having these all at 3 means we're always alpha to a heteroatom. Oops, did we mess up here on our structure?
Extra carbon.
Yeah, Isaac was going to catch that for me. Okay, so there it is, the tert-butyl and then 3 methylenes, which is consistent with all the rest of the day. And these are harder problems, I think these 2 have done, but I think stepping through the data and letting you see how I approached the problem and using all the data, but then we went back and checked things to make sure we're internally consistent, and we caught that one problem, or Isaac did, on the degrees of saturation. And here too, we could, rule out some possible structures. This may not be the only one. What if we add all the methylenes together? We should see that this would be incorrect as well. Okay. Now that's a hypochlorite functional group. That's not one we've covered, but that puts the 3 methylenes all together there. These are actually known, these hypochlorites. Very reactive though. But this has the wrong shifts. Again, these would be further what? Upfield. And they have different multiplicity here too. This would not be a clean singlet or triplet at that point, right? That would be a quintet. So then the multiplicity is off there. But anyway, go back and check your structure to make sure it's internally consistent. This one is correct, I think, for the data I showed. Oh, you may be asking, well, which one is which? Alpha to the oxygen or alpha to the chloride here? Sometimes that's hard to tell. Which one is more electronegative? It's actually the oxygen. So I think this is the one here, alpha to the oxygen. The chloride is actually this one, I think. But if you mix that up on a test or whatever, we give you full credit. Okay, so it might be a little difficult to sum this, but they're both in that same 3 region. Anyway, is that helpful? Okay, very good. One other thing I want to do before we go to the sample test is work some synthesis problems. And these are good because these combine multiple reactions, right? So let's see, can we take butane and somehow get to 2-butanol or selectively get to 1-butanol? How do we do that synthetically? Okay, think about that one. Let me get another one up here. How can we take allyl alcohol and get to this chiral diol with that stereocenter in place? Let's see, what can we do there? You want to pause and work on that? You can. And let's see, we are back. So let's figure this out. What do we need to get on this alkane? We need to get something on there. And your best friend here to start these type of reactions out is bromination. In fact, these halogenations, those are the only reactions we know with alkanes. So start there. This gives us a handle on the molecule, right? We got the isopropyl bromide, and that's it. Don't try to make the primary bromide here. This only makes the 2-bromopropane. How could we get that to this alcohol? Well, that'd be easy. Sodium hydroxide. What reaction is that? SN2. Small charged nucleophile, secondary, is slower than a primary for SN2, but that works. That's a way to make isopropyl alcohol. How do we get to the primary alcohol? Now that one's a little bit different, right? What do we need to do? We need to eliminate it with sodium T-butoxide or potassium T-butoxide to the alkene. And notice that's a way to go from an alkane to an alkene. Now, how do we know how to get to the primary alcohol? Right, hydroboration. Okay, so this is combining a couple of reactions from chapter 10. And that's okay, but this first reaction here for our synthesis is what, chapter 15. So combining these with other reactions, that's fair game, but again, here on test 4, we'll always have one of the reactions from this chapter sequence 12 through 15. But we could have you need to use some reactions from previous sections. And again, on the final, these reactions are cumulative that way. Okay, what about this one? Allyl alcohol going to the chiral diol there, where that stereocenter place. Well, you might want to think here, we've got a substrate for sharpless, okay? And we could just say sharpless, very sharpless. It's the name of a guy, capitalize it, okay? Or draw out the reagents. And you can pick dextrorotatory plus DET or minus DET, whatever, or show the titanium and the terbutyl hydrogen peroxide, or just say sharpless. And what are you going to get here? You're going to get the chiral epoxide. And it'll have that stereocenter in high in antiochurity. So how can we go from that epoxide to the diol? There's a reaction we just reviewed, right? What do we need to do? Lithium aluminum hydride, LAH, sometimes it's abbreviated. And that hydride can add where? At the terminal position. Pop this open, then we've got to quench with water. Okay? So this is a way to go from the alkene, of course, to the epoxide, enantioselectively selectively due to the sharpless reagent. And show either one, but show the one that here corresponds. That stereocenter there corresponds to that. And once we form that from the epoxidation, you see, opening up here, that's not a stereocenter. We're just going from this methylene to the methyl on the end there, okay? So there's a couple of synthesis problems. Let's do a couple more here. Let me get them up on the board. And you can practice them. Come up with your own answers here. Let's see. Can we take this methyl cyclohexane and somehow get to this? Diol looks like that, and it's racemic, okay? Or can we get to this? So kind of a double one here. Can we get to this hydroxyketone? Oh, now that's a little more complicated. Can you get to either product from this methyl cyclohexane? I think you can. How about this problem? Let's take methyl cyclopentane and see if you can get to this aldehyde ketone. Okay, there's your challenge there. And can we take this allyl bromide and get to this unsaturated ketone? I guess you already got the alkene in there. Okay, take a minute and see if you can come up with those 3 synthesis solution problems. Okay, and we're back. So how are we going to do this? These are both alkanes, right? So what do you think we need to start with? We've got to functionalize both carbons somehow eventually, but starting out with what? Bromination with light on both of them is how we're going to deal with this. Okay, but look, to get to this diol or this ketone alcohol, we've got to functionalize both carbons here of the cyclohexane. So how can we convert this into something that might lead us toward that? Right, t-butoxide. What are we going to get now? We're going to get the alkene there. And either side is symmetric, okay? Now how do we go from this to the diol here? It is chiral, but it's racemic. Yep, osmium tetroxide. And that's all you need to show. Osmium tetroxide and water actually to quench that, but the alcohols form on the same face, either the top or the bottom. I'm saying DL there, so the enantiomer of this would have both alcohols down, right? This one leads to this one. That was kind of a swindle there. How do you convert this dialcohol to this ketone alcohol? Well, what do you recognize here? Tertiary alcohol, secondary alcohol. Which one do we need to oxidize? Right, the secondary one. Tertiary one's still there. Well, all those oxidation conditions we've been talking about do not oxidize tertiary alcohols. They stay there, they're unreacted. So we can just say PCC here. We could say chromic acid also, probably get a lower yield. It might cleave this bond, it's a little more aggressive reagent. The PCC would cleanly take this to just the alcohol ketone. Okay. Same thing here on this one. We'd have bromine and white. Then we'd get the bromo product, monobromination. And what do we need to do here? We need to do the same thing, t-butoxide. So very, very good reagent, right, for making alkenes there. And then what? We've got this. And then what's the next step? Ozanolysis. Okay. Completing both of those, we get 1, 2, 3, 4, 6 carbons. 1, 2, 3, 4, 5, 6. Yep. This one became the aldehyde, and this one right here with the methyl group becomes the methyl ketone. Okay. So yeah, that one's not as bad as it looks. If you kind of go backwards, and if you remember this key reaction here, the halogenation of alkanes. Then we got this one here. How are we going to get to that ketone here? Well, what can we do with allylic bromides? Bromides are good leaving groups, right? So let's treat with sodium hydroxide first. SN2 reaction, right? That will give us the allyl alcohol. And then what? Well, PCC again. Okay. And that will give us the product there. So again, combining some previous reactions with reactions from chapter 12 and chapter 15. All right, let's go to the overhead up here and go look through the sample test. And I've got the worksheet solutions as well. You might have questions on that, and we can go through these and see what you'd like to talk about there. First page, I don't know, some of those that are a little tricky. Number 1 might be a little tricky, hydrogenation. Which one gives off the most heat when these are hydrogenated? Well, that would be the less stable one. That would start out at the highest energy point. And which one is the least stable? Well, yeah, the mono-substituted one. Okay. Primary alcohols react, carboxylic acid, we've been reviewing that. NAD plus is what? An enzyme cofactor involved in oxidation reactions. Now the other cofactor is what? NADH. That has an extra hydrogen on that pyridine ring. That does reductions in nature. NAD plus is the pyridinium form that actually can accept a pair of electrons and a hydrogen atom. And so it undergoes a reduction and it oxidizes substrates. So it's involved in oxidizing the reaction itself. And the one we talked about there was converting ethanol to acetaldehyde. That primary alcohol in ethanol can be oxidized to the aldehyde. This one's chapter 15, obviously, the allylic radicals involved here with NBS. So certainly number 1 would form allylic bromination at the more substitute spot. But notice you have the double bond here and the radical there, the resonance structure. So you'd also form some of 2, I think. Yeah, those are the 2 products, 1 and 2. This one, you're not going to selectively react out there. That's an alkane. Here we're talking about allylic substitution of NBS and heat or light. So yeah, it's just 1 and 2. And some other definitions there. LAH, like we talked about, opening up epoxides. Yeah, I'm not going to give too much detail on it. I'm just going to kind of pick the harder ones here. Which compound possesses N plus 2 peaks with a ratio of 1 to 1? Yeah, that's the bromo product right there. We talked about the halogen isotopes. And here we've got what? A carbonyl in the IR at 17 or so. And hopefully you'll be able to read these. We'll make sure these are very clear for you. And then we just got CH alkyl stretch. There's no alcohol here, for example. So it's not an alcohol or a carboxylic acid. Must be a ketone. Yeah. And then we got picking out multiplicities. So there's a lot of ways we can ask NMR questions. In this one, you're asked about a quartet. So if it's being apparent as a quartet, you got to subtract 1 to get back to the number of neighbors, right? So it must have 3 neighbors there, the N plus 1 rule, to make it a quartet for its multiplicity. So which signal has 3 non-equivalent neighbors? Well, this one has 3 neighbors here, but it's symmetric here. There's 3 neighbors over there for a total of 7 for that pattern, right, for isopropyl. So it's not that one. But here we have an ethyl fragment. And an ethyl fragment is what? A triplet and a quartet. This one right here is a quartet because it has 3 neighbors. This one's a singlet, and these show up as a singlet here. So the monosubstituted benzene, no. Definition of NMR, the frequency here is radio frequency. Nuclear magnetic resonance, the magnetic nuclear spins are resonating in the radio frequency range, which is the very low energy, long wavelength range. We went through that for the basics, the background of NMR. Infrared is a much higher frequency, shorter wavelength. X-ray is extremely high frequency, very short wavelength. Remember, they're inversely proportional. Microwave is kind of in between the two there. This one's a little bit trickier one, I think. The topicity thing, classified as what types of hydrogens right here, the 2 that are indicated. Are they the same? Are they homotopic? Are they an antiotopic if we exchange these with 2 different deuterium at the 2 spots? Are they diastereotopic or gyrotopic? That's a made-up word, sorry. Diastereotopic, if there is a stereocenter, these 2 hydrogens, if you sequentially substitute them with deuterium, you come up with a pair of diastereomers because of the existing stereocenter. So this will always have different shifts and different coupling patterns. So they're diastereotopic. Molecule's deceptive because it's a relatively simple molecule, but you should be aware of this topicity problem. Look for a stereocenter, and then in theory, all the methylenes are diastereotopic. Another NMR question talking about multiplicity, a singlet, and the shift, 2.2. So this would be singlet, though. This would be around 0.9 ppm alkane. Aromatic, that's up at 7. Alkenes at 5. So which one would be a 2? Oh, the benzoic hydrogens here. They're shifted a little bit downfield, but they're not directly on the benzene like this one. These are at 7.2. But adjacent to the benzene, a little bit further downfield, 2.2. Okay. Let's see, we talked about the structure of the radical trigonal planar. Initiation steps, so you should know the difference between initiation and propagation. The initiation step involves hemolysis of the halogen bond to make the halogen radical. Right? Basis for selectivity, we just talked about that. Okay, it's because endothermic for bromine radical. Okay. Which alkane reacts with light, giving 4 structural isomers. This one's a little tricky. So this one here, you need to spend some time with scratch paper and draw out all the possible monochlorination products, light at room temperature. So we're talking about monochlorination. So which one? This one would give 1, 2, 3, 4, 5 products. This one would give 1. The 2 ethyls are the same. 1, 2, 3, 4. B looks right, but make sure you check all of them, right? All three in the terbutyl group are the same, so that'd be 1, 2, and then 3. And this one, all these methyls are the same, so 1 and then 2, and then 2 methyons are the same. So I think this one is the one with the 4. But draw them all out. Okay, use your scratch paper and check it out. Mechanism for allylic trapping with BHT, butylated hydroxytoluene. That's this aromatic group with what, a phenol right there. That's the food preservative, remember, that shuts off allylic oxidation. And the key there is the allylic radical. I'm showing the trans thing. This would be like a trans fat. And what do we do there? Are we coupling two radicals together? No, that would be low probability. Can we take a radical and then what? Grab a hydrogen atom off the BHT with an OH right there? Yeah, C is the correct one. The others are heterolytic reactions, which is not involved in allylic oxidation. Then we have a polymer one. And you can see here the polymer. I think there's 3 monomer units shown. And alternating our methyl groups skipped the 1,3 position. So that must have come from propene. So this is polypropylene, okay, with the radical initiator. This one here is methyl, 2-methylpropene. That would have 2 methyls alternating in each spot there. Ethylene wouldn't have any methyls showing there. It'd just be the straight chain hydrocarbon. Styrene would have the benzenes there. Okay, signal here. Oh, this is another one with a stereocenter right there. The signal for the proton indicator will appear as a blank. This hydrogen will be coupled to these 2, and these 2 right here are diastereotopic because this is a stereocenter. So it'll be a doublet to one of them and a doublet to the other one. They have different splitting, different patterns. So doublet to doublet is correct. It's not a triplet. These are not equivalent, these 2 diastereotopic hydrogens, because of the stereocenter. So that one's a little tricky. You need to know topicity, especially talking about diastereotopic. You have a stereocenter, the 2 hydrogens on a methylene group will have different shifts and different couplings. Mechanistic rationale for anti-Markovnikov addition here, formation of a more stable radical intermediate. Yep. So review that mechanism there. Well, we involve initiation from forming a radical there. The radical from the initiator extracts hydrogen, and then the bromine radical adds to the alkene on the end. Ozone can undergo radical degradation of chlorofluorocarbons. Oh, that's one I just told you to read. I just mentioned it in class. The ozone layer in the upper atmosphere is a protective layer. It filters out damaging UV rays from the sun, which can be ionizing, very dangerous to different plants and animals on Earth. And these fluorochlorocarbons were used as refrigerant molecules for years, and they built up in the upper atmosphere and started to degrade the ozone layer. So luckily we could detect that and correct that. We don't use chlorofluorocarbons or CFCs anymore for refrigerants. We use compounds that are benign to the ozone layer now. So it's a great example of environmental monitoring and change in industry to switch away from those damaging. And that's just a definition thing, reading from the material. We will have a couple of those application things on this test, so make sure you read those things, and if I mention it in class and it's talked about in the book, it's more likely we might cover it. Here's the reactions from the sample test. We've already worked some of these that are similar. You can look through that. We've got questions about those. I'm not going to do each one now. I think a lot of these are straightforward. Chlorination. There's the anti-Markovnikov thing there. That's probably the toughest problem in chapter 15. So it'll be ones like that. That gives a mixture of 2 enantiomers. Allylic bromination, you got to draw out 2 different allylic radicals, and I think that's exactly like one we did on the board. And here's our old friend, monobromination of alkanes. Keep this straight now. Brominating alkanes is different than allylic bromination of alkenes. So 2 different reactions. That can be a source of confusion there, keeping this straight. Here's another way to ask questions, and again, it's all multiple choice on our test 4, but there's different ways we can couch these problems, right? We get a multiple choice. where you got to pick the right combination of reagents to go from starting material to product. And so we did some of these synthesis problems already, and some might need reactions from previous chapters. So you can look through those and see that those are very similar to what we had there. I like this one here. How do you go from a transalkene to a cisalkene? That one is kind of good to work backwards. So here, how do we get to a cisalkene? Well, there's only one reaction, the Linlar half reduction, right? So we go back to the alkyne here, and there's our Linlar thing. How do we go from an alkene to an alkyne? Well, yeah, we brominate it and then do 2 E2 eliminations to go from the dibromide after we brominate, and then 2 E2 eliminations goes to the alkyne, and then we Linlar it, okay? So that one looks very deceptive, but if you go through it stepwise, it's not bad. And here we are, MCPBA, the epoxide. Open up the epoxide with an alkyne nucleophile, and then reduce that alkyne nucleophile. We have an alkyne there. And now we do the sodium ammonia reduction there, which puts the trans double bond there. So I think those two are kind of the trickier ones. Then we got this one, and this is very similar to one I think in the book. Here you got the reaction. You're told 3 isomers, and here's the data, proton NMR for each one. Here, just draw out some isomers. Think about the reaction and what are the possible products. So start with what you know from the reactivity there. You can have this dichloride or the 2 chlorides together or the 2 chlorides on the end. And then you start thinking about the multiplicities of the patterns there. And then they really line up quite quickly. They're really simple NMR problems once you get to that point. But you can clearly see this one here as a doublet, and they're both the same. It shows up as 6 hydrogens there. You're given the integration, which we normally do. We left them off that problem 2 on quiz 9, because there you could just rely more on the shift values. But here you're given the shifts and the integrations, which help out. Of course, you see the multiplicities. And here you got the 3 signals. You got your quartet triplet, so you know you've got an ethyl group, and then you've got an isolated methyl here, singlet, but it's alpha to 2 electronegative groups, so it's a little bit further downfield. And this one here, they're both on the end, so that one there is, way up at 5, and it's got the 2 neighbors, so it shows up as what, a triplet? Yeah, and I think you can analyze the rest of that there. And again, we can convert those into multiple choice type problems pretty readily. This one's similar to one I just worked on the board, I think. You can see the main fragments here. You're given some mass spec data, and you're given the molecular ion and the M+2 ion there, so and they're 1-to-1. So yeah, bromine. And that lets you play around and figure out your formula here pretty quick, which turns out to be, well, I'm not even showing it here. Oh, well, you have the C13 too. And from this data, I think you can see an isopropyl thing kind of right away, and then a methylene here, and then a couple more methylenes, so you have like an ethylene in between the 2 here. They're both triplets, so you've got things on both sides there. And then, yeah, it's an ester, so yeah, this one here makes that guy from the isopropyl very complicated. Multiplet, it's okay to call it a multiplet. Yeah, the other pieces go together okay there. It's not too bad, but yeah, thinking about how many carbons you might have and then adding up the hydrogens gives you an idea of what the structure of the fragments might have. Now this is a harder problem here. This involves some steps and reactions we did not cover at all in chapter 15. However, we talked about peroxy compounds and how they're initiators. And we show this here, and how the peroxy thing can break down to the carboxyl radical, and that can make CO2 and this alkyl radical, okay? So that's just pushing electrons a little bit more beyond what we showed you. And so here's the rest of the electron pushing. You get that alkyl radical. And that alkyl radical can grab a hydrogen atom from the starting material to get this type of product here, okay? That's A, okay? And B, how do you get this? Well, 2 of these could couple together. And you're not told the relative amounts here of these. This is actually a trace material. 2 radicals coupling together to make that. You could get to A and B. And then this one here, these cyclic ones look really strange, but we talked about radical additions to alkenes, either on the N carbon here, and then this hydrogen atom going on to that radical. And this hydrogen source, this RH here, could be anything along the starting material here. So we're not precise about all the parts of the mechanism here, but you can cyclize this way or cyclize that way to give the cyclohexane or the cyclopentane, right? And give the different C and D. So there you're given the products and you're just using the mechanism to get to those products. So obviously not a reaction you covered, but based on the principles we've taught you, you can actually figure that one out. Now some of the worksheet problems, a little bit harder. A lot of these kind of follow what we've already been talking about, so I'm not going to go too much there. I think you should be able to figure these out okay. Let's see, and here's the sharpless deal and a couple of them. There again, you don't need to know which enantiomer you're going to, just show either form of the DET. We'll stick to DET, there are other tartrates that are used actually. Here's some ones we just covered, similar types of multi-step reactions there, some eliminations and halogenations here. Here's converting the alcohol. You could use phosphorus tribromide there, do the same thing. And then ozonol, or osmium tetroxide gives that diol. Okay. Yeah, so that's kind of the same thing. Here's a couple different mechanisms that if you follow the principles, LAH open and up the epoxide, and then the generated O-, doing an SN2 intramolecular on the chloride, gives the cyclic structure. Here we're adding peroxyanion, which gives this new peroxy thing that can break down from the enolate and form the epoxide right there with loss of hydroxide. That reaction is kind of more suitable to 352, but again, you're given the product and maybe given some hints about that. That would be a hard mechanism on its own without knowing too much about that. But we've talked about peroxides and what they can do. You can kind of piece that one together. This is a neat one here, cis to trans, and we talked about how to do that. I think that's the way to go to the trans fat that are known materials. 13 here, more on spectra, coming up with different structures. Yeah, I think you can see how that works okay. Spectral data here, what are going to be, oh, don't worry about the fragments. I'm not going to test you on fragmentation. Sometimes you'll see those fragment data there, but some of this I'm showing where these things can be cleaved like a halide. You often just use the halide and form the carbocation, and that's just loss of chloride, a loss of 35 there. Alcohols cleave at the alpha position normally, but yeah, there's some molecular weight for that. Same thing for this one, series of compounds here, and loss of 15 is loss of a methyl radical. CH3 has 15 atomic mass units, and this one right here is the common one for losing that, because that gives a more stable secondary carbocation. Here's the drug testing thing, which really just goes to the molecular weight, I think, of that. What type of mass spec data, 315, you can just add up the molecular weight here of the carbons and hydrogens, and it turns out the guy OD'd on OxyContin. And there you go, that would be a typical test in the lab to figure out which drug. Cocaine would have 1 nitrogen, so it'd be odd, the molecular weight, as well as methamphetamine. And you're told here the mass is 315. Oh, and OxyContin also has 1 nitrogen. So yeah, you can't just go off the nitrogen rule there. But there you have to add up all of them. You can also tell by NMR and compare to the standard. Here's one that's a little bit tricky, I think. You're given data here. It's just mass spec. And these two way up here, even, 1 to 1, 2 apart. It's probably bromine again, and then a carbonyl and CH, that's all you've got there. But you got the carbonyl and this mass here, 180, you can get to this molecular formula, I think. 2 oxygens means you probably have an ester. This would be a structure consistent with this data, but it may not be the only thing we'd use, right? We'd use NMR to figure out if that was the true thing based on the shift in multiplicity. So that's just one of a number of possible structures there. And then NMR, Equivalent sets, I think a lot of these are pretty straightforward there. Oh, this is a topicity thing. So here you just sequentially exchange the two hydrogens for deuterium, generate two structures, and then see what the relationship is between those two deuterated structures is. And diastereotopic and antiotopic, homotopic, this has symmetry to it. Diastereotopic, there's two stereocenters here. Same thing with these others, you can go through that. Again, if you come to a diastereotopic relationship, they'll be different in the NMR and be more complicated there. How many sets? I think you can go through those there. Predicting the multiplicity patterns, that's often a good thing to start out with. Proposing structures, these are similar to problems in the book, I think, coming up with those. This one's a little more complicated, and it's got a nitrogen in it. And look, the mass spec data, 115, it's odd. So you know you've got one or maybe three nitrogens. So that's a way to figure that out and get started. And then you got a diastereotopic pair here, both multiplets, and that's that position right there. This is a alpha amino ketone that has two ethyl groups on it. And it's consistent with that data, except for the topicity. This one, number 5, is tricky because it's highly symmetric here. And it looks like in the C13, you've only got 4 carbons, but they're both the same here because of the symmetry in this ether molecule. You know it's an ether because there's no 1700 in the IR, and the mass spec consistent with that, and then the fragments. This is an inset blowing up this so you can see those multiplicities a little better. And you just see you have the N-butyl things on the side here. You have terminal methyls, and then you have methylene way down here, alpha to oxygen. That's a triplet with 2 neighbors, and then the guys in the middle, complex multiplets. Those are hard to figure out, but 3 to 2 to 2 to 2 means it's probably a butyl fragment. And then you have the 2 here, gets you up to 130 for the molecular weight. But the symmetry makes that one a little trickier. For chapter 15 worksheet, some of these reactions here I think are okay. Bromination with the alkanes, just always go to the more substituted one. Allylic, always draw the multiple allyl radical intermediates. And I think those are okay. Anti-Markovnikov versus Markovnikov here for that. Yeah, the others are okay. I think the mechanism, we went through that. Oh, the selectivity and calculating or estimating the percentage here. I did not show you how to do that. This problem kind of leads you through it. It's a weighted average, and you see what the total percentage is for that weighted average. I'm not going to take time now to discuss that. With chlorination, it's always a mixture. So here, iso octane, and we did this one, and I actually gave you these percentages. But here I show you how you calculate that with a weighted average, but don't worry about that. It gives a mixture here. If we use bromination here instead, you get the one product there, bromination right there, which would correspond to that product. That would be 100% bromine. Okay, allylic oxidation here of linolenic acid, which has 3 double bonds. They're all cis here, and you're asked about the mechanism for allylic oxidation. So here is oxygen abstracting an allylic hydrogen, that one right in the middle. Well, there's 2 methylenes right in the middle, which will give highly delocalized, stabilized allylic radicals. That's where things will happen quickly. These polyunsaturated fats go rancid quite quickly if you leave the cap off. Always keep them tightly closed in the dark. If they're out in the presence of oxygen, with light especially, they're going to go bad pretty fast. And there's the allylic peroxide that can form there. It'd be slower on the other sides there. Much faster than oleic and stearic. Stearic acid doesn't have any double bonds. It's very stable. That Crisco lard material used for baking, that's stable for years in the pantry. Anyway, but yeah, that reaction, resin stabilized radical. And then we have some other polymers here. Polyvinyl chloride, that's one we did. The 2-methylpropene, I think we did that one too. The cyanofluoride, that's a different one, but again, you just see the monomer units and then how the initiation and how the differentiation might go. The initiator always adds to the end and gives a stabilized radical. A stabilized radical adds to the end of another one. That's why you get the 1-3 skipped relationship. So it kind of comes out of the mechanism. Okay, and I think that's it. Yeah, that's through all of them. If you got more questions on any of them or any of the homework problems, shoot me an email and we can help you out there. But good luck on test 4, and we will see you next time. We'll also have a final review class video coming up. We'll post that also on Learning Suite. So very good. Good luck on test 4. We'll see you next time. Thank you.